I'd like to welcome everyone to the webinar series of the Cybersecurity and Information Systems Information Analysis Center, CSIAC. Today's presentation is entitled Cybersecurity for Energy Systems. My name is Steve Warzala. I am the CSIAC Outreach Manager. A few administrative notes before we begin. First, all phones have been muted except for the presenters. Questions may be asked at any time during the presentation by utilizing the chat function. And time permitting, your questions will be answered at the end of today's presentation. I'd also like to take a moment to acknowledge and thank our sponsor, the Defense Technical Information Center, DTIC. Funding that DTIC provides enables CSIAC to conduct these webinars. It's my pleasure to introduce our presenter for today's webinar, Mr. Tim Watkins. He is the lead application engineer for Schweitzer Engineering Laboratories, SEL. Tim works in SEL's Secure Engineering branch of research and development. Tim is supporting the development of an architecture which will reduce risk and increase resiliency for control systems. He has been significantly involved in the development of an operational technology software-defined networking switch. Tim will discuss how this technology can increase the usability and performance of a network, as well as raise the cybersecurity and visibility of the network. I will now turn the presentation over to Mr. Watkins. Good morning, or good afternoon, Tim. I guess it's morning where you are, and the floor is now yours.
Hey, good afternoon, everyone. It's definitely still morning here on the western side of the United States. Thank you, Steve, for the introduction and the opportunity to speak to everyone. Today's webinar will be focused on SEL's involvement with Department of Energy's Cybersecurity for Energy Delivery System, or CEDS. I will start by giving a quick overview of Schweitzer Engineering Laboratories, highlight some of our involvement with federal agencies, kind of goes through why CEDS was created by the Department of Energy, and then go into some of SEL's involvement with this program, and then why I think one of our CEDS projects, as Steve already stated, operational technology, software-defined networking, is a potential game changer. At SEL, we have a core belief that everyone should have access to safe, reliable, and economic power, regardless of where someone lives or their social-economic status. I look at power as the most critical of critical infrastructure. Without it, mission assurance in a DoD environment is severely degraded. Imagine a base, whether forward or deployed, loses power to water, sewer, and fuel pumps. I can think of examples in Fallujah where we lost power to our HVACs and had to shut down Nipper and SIPRNet network for the risk of server rooms becoming too hot. So it's definitely a high mission assurance, high impact capability that must be really thought with reliability, cybersecurity, and so many other things. Kind of a little bit of a bottom line up front about who Schweitzer Engineering Laboratories is. It was founded by Dr. Ed Schweitzer, who is obtaining his doctorate at Washington State University here in Pullman, Washington. And his doctorate involved the creation of the first digital relay. He began working in the garage with 12 others to build the first relay. And where this became powerful was that this relay was used to protect transmission lines that had to be previously, if there was a tree that fell on a transmission line, you would have to fly a helicopter hundreds of miles over the top of all this infrastructure to figure out where the break happened. Now, with Ed's device, it did several things. One, it contained a distance element in it that allowed you to figure out where that break happened, so that you would instantly know within about 100 to 300 meters where the break happened, so you could go out and restore power faster. And then not only did it do the fault location, it also recorded why that decision was made so that the utility could determine root cause of the event and then fix that problem so it didn't happen again. And since that time, we've continually identified, measured, and improved our devices over time. In order to do this, we need mission-critical precision, the combined data intelligence sharing. So I'm going to step back there. Some of my slides changed here. SEL is pushing the envelope in
Tim, we're having some trouble with your audio. Is everything okay out on your end there?
I'm not sure what happened there. Let me back up one slide and see where we were. Where did you lose me at, Steve?
Let's see. You were on slide 5 and you kind of dropped off there.
Okay, sorry about that. Our focus on engineering investment in R&D and our culture of creativity leads to breakthrough technologies to focus on the physics of power. Energy moves at the speed of light, and protection systems have to be fast in order to make these decisions quicker. Applying new principles to protection has resulted in tripping times that are 10 times faster than phaser-based protections that we used to have. To put this in context, as a general rule, for every 1 millisecond that you can reliably trip faster, you can put about 10,000 more households of power over that same infrastructure. One of Dr. Ed Schweitzer's favorite stories he likes to tell is the fact that power is moving at the speed of light and that communication through fiber is about 30% slower because of refraction. This means that when devices need to communicate, a power event is happening faster than the communication. It creates interesting issues when performing cyber communication and control while trying to prevent cyber failures and attacks. In order to do this, we need mission-critical precision. The combined data intelligence created by sharing data among intelligent electronic devices creates a true awareness of the power system. This unique capability represents one of the most valuable modernization efforts possible. In most utilities, this is a low-hanging fruit for return on investment because most systems are not taking advantage of these existing features in-service devices and actually use only a fraction of the network's capabilities. These systems make greater use of smart product characteristics built into the intelligent electronic devices to create a system capable of making observations and decisions and then taking action. This contrasts with current available systems that simply provide a snapshot of present values with no opportunity to understand trends in power system activity, system performance, or apparatus degeneration. Over the last 9 months, I have spoken in over 10 countries and hundreds of OT folks about cybersecurity, and I've discovered something. The majority of these people are already doing risk management. They just don't call it that. The amount of detail put into a design, implementation, factory acceptance test all creates plans, policies, and procedures that fully make sense to a power or automation engineer. It's tying the same methodology that they already do to cyber. Cyber that should not be stovepiped from the risk management or the operational management that they are already doing. It must be looked at holistically, and then no matter who you are, You have a finite amount of people, time, and money, and that's really where it comes down to on what risk that you really take care of. It will be different for a utility to think about cybersecurity if they are 10 years behind in trimming vegetation away from their power lines. The transient faults or the branches touching power lines that causes momentary losses in power or short blackouts will rate much higher with the business impact analysis than the cyber events. Should a utility put less money into factory acceptance tests to make sure that the control system operates during an event so that they can hire an incident response team? Probably not, but that is the direction that they're going to have to eventually grow. But if they realize that there's cross overlap between the people looking at the HMI for the power system is also the same people that should be aware of everything that's happening in a normal system information event management system or intrusion detection system. If there's, and also include in that the physical security of their locations, it can all come together as one holistic solution. This also brings into context that these devices are made to operate for decades with engineers that have worked with them for entire careers without a cyber event. Granted, they may have a lot of events that they never reach root cause on, but they also don't have the tools to discover if the event was actually involved cyber or if it was just something that the system was never proactively engineered to solve. From a vendor's perspective, we have the same issues of people, time, and money. We support North America and all federal agencies. If you were to go in any substation in North America, 70 to 80% of the intelligent electronic devices are blue SCL boxes. The international community is also increasing. With this comes a myriad of different security frameworks or compliance regulations to follow. Daily, we are asked if our products have been tested for this or certified for that. First, if we were to design our products to be compliant with every security framework, the price, complexity, and attack surface would greatly increase beyond a device that follows common sense. What we do like is when we see charts like the SANS CIS security controls. This PDF maps NIST 853 security controls to over 20 other security frameworks. As we work closer and closer with DoD and federal agencies to type RMF our devices in a generic system, we have noticed a significant overlap between these frameworks to the security controls found in the risk management framework. Reciprocity in the risk management framework is key. And between security frameworks is key to both DoD and to vendors. DoD benefits that from an SCL type RMF ATO by reducing the time and cost of site ATOs. SCL benefits because this type RMF will allow us to report our plans of actions and milestones to a single authorizing official. If we were to try to manage this at the site ATO level, priorities won't match. And if everything is a priority, nothing is a priority. What I have noticed from taking off my uniform is that the internal and external cost of all the different requirements does significantly increase the price of a product. I know one vendor that uses the exact same devices for both DoD and non-DoD customers. DoD customers require FIPS 140 Level 2 for wireless communication. Also, they have to have JF12 for CONUS and OCONUS. He places a sticker on the device and sells it for $1,000 more than non-DoD to absorb the cost that's required to maintain FIPS compliancy. When you add JITC, NIAP, disapproved product list, the time and cost required for each it grows. And as a community, we need to ensure we are doing the right thing, especially when some of these processes take 9 to 24 months of delay to get our product out to market. I created this slide to highlight some of the differences between IT and OT networks. We're asked this quite often. In an IT environment, devices typically last 3 to 7 years. At the 7-year mark, systems are replaced and the latest and greatest enhancements and cybersecurity best practices are purchased. OT, a device is typically online for upwards of 25 to 40 years. OT devices remain in use not only because of the price of the device, but the amount of time to design and install and ensure that that system will perform as it's supposed to in such a short amount of time. Availability in an IT system is orders of magnitude higher than OT. If I don't get an email or access to a website in 200 to 300 milliseconds, I might not even notice that the switch failed and traffic was rerouted with a spanning tree algorithm. However, in an OT, that's over 15 cycles of power, an event that could cause loss of power over a wider area, damage equipment, or cause an arc flash that could significantly destroy equipment or injure someone. In IT, we can afford milliseconds of latency in communication channels. Some traffic in OT have time to live of 2 milliseconds. If the protection signal doesn't make it in there and under that time, it'll be considered old news, irrelevant, and dropped. One significant advantage of OT systems is that I'm not dealing with thousands of users and thousands of applications that have dynamic communication of who's communicating to who and what machine is communicating with who. An OT system is purpose-built and proactively engineered. When a user logs in with admin or engineering access rights, it should be considered a significant event. Typically, a relay will only will report to one or maybe a few other relays with protection traffic and be monitored by a PLC with automation traffic every few seconds. Traffic outside these norms should be identified and looked into. User access should be very well coordinated. Even logging into a device should be brought to the attention of the security or the network operations center of, was this on the change management and control board to happen at this location today? This slide shows an example of SEL's secure reference architecture. We use this to highlight some key areas. It was developed with USACE and OSD level, and has been used in several of the reference diagrams, but this one's kind of a simplified version. It is very important to segment OT from IT, creating a DMZ between OT to IT for information that may be required by IT to do their job, and then segmenting human-to-machine traffic of layer 4 from machine-to-machine traffic of layers 1 and 2. In layers 4 and 5, you have workstations and servers that require much higher confidentiality and should be operated, maintained, and secured much the same way that you do in an IT network. However, the lower you go in the energy control system, you will have to sacrifice some confidentiality in order to increase availability. Think of that protection traffic that must arrive in 2 to 16 milliseconds. And the earlier arrive, the better it is for the system, the quicker the decision can be made. Using strong encryption on this type of traffic does not make sense, especially if it never leaves the physically controlled substation. However, encrypting and authenticating traffic from a remote user from the human-to-machine level does. From the start, SEL has been involved with federal agencies. We've been doing this for decades with the Department of Energy, DHS, DOD, and many other three-letter agencies. We have also been working with OSD, USACE, U.S. Army, and U.S. Marine Corps in that effort to get that type-level ATO for our products. This has led us into being proponents of the NIST Cybersecurity Framework and the NIST Security Technical Implementation Guide. At an SEL enterprise level, we are using these STIGs and security reference guides to develop new and current products to be more secure. The security controls from them are being integrated into our product design specifications. Some of our latest efforts have been working with the USACE, Army, and Marine Corps on a tactical microgrid. This has been something near to dear to me with my 4.5 years of deployments to Iraq and Afghanistan and other places. The systems that we used during OIF and OEF were not reliable and only manually redundant. A lot of fuel and generator parts are wasted by not using power efficiently. From the second I started working at SEL in 2013, I knew they had solutions at a forward operating base could use to save lives and reduce fuel consumption. A solution that could also greatly increase the resiliency and increase mission assurance of forward operating bases. Over the last year, SEL has been involved in the standard consortium, and we now have a working system that can take multiple types of generation and control them based on changing loads. This system could be at a company or regiment level without the need of a power engineer and could grow or shrink depending on the demands of the military operation at that time. SEL has been involved with another Department of Energy activity. The first one that we were involved was with NREL, and NREL is the National Renewable Energy Laboratory by the Department of Energy, and they did a shootout where there was a competition between different vendors for creating a microgrid, and it was a 21-week exercise that SEL ended up performing the best, and that was the microgrid that was now used for NREL. And another project that we've done with the Department of Energy since about 2008 is the Cybersecurity for Energy Delivery System. The goal of this program is to align Department of Energy with federal priorities and milestones articulated in the energy sector roadmap. You can Google CEDS or type in the link below to obtain more information. The CEDS roadmap began back in 2008 and was updated again in 2011. It contains the milestones Department of Energy would like to achieve by 2020. The vision is to have a resilient energy delivery system capable of surviving while sustaining critical functions. This is done by the 5 categories listed on the left: building a culture of security, assess and monitor risk, develop and implement new protective measures, manage incidents, and sustain security improvements. I arrived at the OT community only 5 years ago after supporting DoD IT systems for over 20 years. I can attest that these are all important topics in the control system sector, not just energy. I have already alluded to the culture earlier and the need to have sensors and continuous monitoring tools. And I cannot emphasize enough the importance of a defense in depth infrastructure between control system networks and the IT or NIPRNet, and segmenting the communication of human to machine from machine to machine. These projects typically involve 1 or 2 vendors to create a solution, partnering with 1 or 2 public utilities to verify and test the solution, and a national lab to assist in both research and to independently validate and assess the results. To date, CEDS has completed 20 projects and has 27 active projects. The next few slides that I'm going to be going over for is the projects that SEL has been involved with. The first being Hallmark. This project was started in 2008. We worked on this project with Pacific Northwest National Labs and Centerpoint Energy. The goal of Hallmark was to develop a cryptographic method to secure a serial SCADA communication for energy control systems. No matter what type of WAN infrastructure the serial information is being tunneled through, this project would secure it. This turned into several multiple SEL products, including the SEL 3025 serial encryptor and the SEL 3031 serial radio. Both have FIPS 140 level 2 encryption cards, and the radio has JF12 CONUS approval. The seeding randomization in the encryptor card is currently being updated, so the device is currently on the FIPS 140-2 historical list. However, we expect to have the validation completed by the end of this year. The LEMS Project's goal was to develop specifications to ensure vendors create interoperable capabilities, security, and operational requirements into their products. It had involved Sandia National Labs, NRX, and Tennessee Valley Authority. SEL's portion was to create a device using these specifications and we ended up developing the Security Ethernet Gateway, or the SEL 3620. It functions as a substation edge firewall router and is a VPN endpoint that can encrypt communication between substations in the operations center. We further enhanced this device to be a password proxy solution to our relays. The concept being that we have legacy relays that only have insecure protocols running on them, such as Telnet or FTP. Remember, these things are online 25 to 40 years. If a remote user needs to access the relay, they would build an SSH tunnel into the 3620 and then authenticate to the relay using Active Directory, Radius, or RSA tokens. My favorite example of this involves combining the centralized access solution amended by a one-time password. So you type in your password and the 6-digit one-time PIN, and now you have access to the relay. Then the 3620, within the physical security perimeter of the substation, would telnet into the relay. I would say this is, besides SDN, this is one of my most favorites. Remember that machine-to-machine devices is built for speed and availability. One of the reasons why in this environment we see public utilities or others so slow to adopt new firmware is because that it takes so much time and testing and money before new firmware is authorized to be on these devices. You also, so getting even signatures onto that relay would be something that they would be very cautious of. So the goal of this product was to make a malware threat to be safe, reliable operations of a power system. So working in the power system environment and basically avoid blacklisting type antivirus, which requires system scans, decommissioning, updates to the AD, updates to the signatures, and it's still vulnerable to zero-day exploits. In the majority of SEL's devices, the systems are embedded and the operating systems are streamlined and cut to only include the portions that are actually needed to make the device work. One, that it reduces the attack surface area, but two, that allows you to map the processes and the memory portions that they should or are authorized to use. So anytime there's a change to that system, the ExaGuard will notice that something has moved, this memory space has increased, this memory space has decreased, and that is how we develop a whitelisted solution that baselines the system security and provides automated device-level protection against any type of firmware change and modification. But again, this is like an antivirus because we know exactly what's going to be happening on that device. Makes it very difficult on a Windows system or the workstation that you're on right now, because you would have to open up all the processes in the same exact order every time for them to be using that same memory every time. But on a relay or an RTAC or a PLC, that type of device, you'd instantly be able to start those processes in the proper order and do this. ABox is another spin-off of our LEMS project. They wanted, at a substation, you have the physical protection of the perimeter, the fence, the building, and everything else. This was developed for reclosers that are typically on a pole that are in a more of a residential neighborhood. You don't have the physical security or the fencing or the cameras on these things. So this device was a smaller version of our 3620. It's the SEL 3622, but basically being a small form factor that could still take a wide variation of temperature range for outdoor and remote cabinet installations. It also contains some alarm protection measures, such as a physical tamper protection, an accelerometer, and a light sensor, and contact switches, so that if the enclosure was open, banged on, or light got into the thing, then alarms would be sent to the operations center to make people realize that something is being physically done to that recloser. Watchdog and SDN is the one that I'm going to go into more depth at the end of this brief, but this is one of the latest releases that we have from a CEDS project. This started with Ed Schweitzer wanting to push the envelope for performance, but as a side effect, what we ended up was having performance and a very secure device. But again, it's a by default proactive whitelisted traffic engineered networks for OT solutions that doesn't just have to be energy. You could be thinking building automation systems, water, sewer, or other type of networks that you'd want to keep typically on a closed restricted network. Energy sector specific flow controller. So we designed the flow controller. I'm going to go into that a little bit. So I'm going to move on from this one. The next generation of the one that we're working on now is called Chessmaster. And this is giving access to third parties via API into our flow controller to use all that good information from the flow controller. And I'm also going to cover this later in the later slides after this, but kind of just giving kind of a historical overview of the ones that we've been involved with. But this is kind of like a proactive defense. A good example that I'll give here is, say I have my normal operating flows that are required across my network to give normal visibility, normal access, normal read-only access. But I am now in an attack mode where I know that security is more premium to everybody getting visibility. This would allow you to turn flows off at an enterprise level, or the other way around. Maybe we have a hurricane coming or a storm approaching where we know that we need high availability to the system, that at this time, we need to sacrifice security for availability so that people can come into these buildings, connect any type of a laptop into the switches, and be able to repair to get the system back up to do its job. And finally, Tempest is a time synchronization platform project. It's to take multiple sources of time. You can imagine if we're making decisions in under 2 milliseconds, the amount of precision required in an OT system versus an IT system. But this is to look and compare different multiple sources of time and bring them back together to ensure that none of the time sources have been spoofed or compromised. Whether it's a satellite constellation or PTP or IRIG type comparison. All in all, CEDS projects have been an opportunity for SEL to identify, measure, and improve our products. It has created strong relationships between Department of Energy, national labs, and our major customers. The program is successful because the concept that vendors and national labs invent are approved by legitimate customers and independently tested and verified by those national labs. We designed something with the knowledge that we already have an early adopter of that product. Department of Energy is also accommodating to plan changes and gives freedom to vendors and national labs to push the envelope on innovation. Watchdog and SDN are great examples of this, and now I'm going to go further into the OT SDN. SEL knows that protection events typically occur at the same time that communication events happen. When communication that is already not as fast as the power signals has an outage, when we need the protection traffic the most, there's a problem. As an IT network and systems marine, heard the developers talking about fast failover times of 100 microseconds. I really could not press the I believe button until I actually got my hands on the device and tried it. The advertised time is 100 microseconds, but what we were seeing was less than 10 microseconds. I really could not press the I believe button. I couldn't, it was just hard to conceive this. So to the point that I couldn't break the RJ45 connection fast enough to do a clean break to get a consistent measurement for my demo. We had to do this with link breakers. And what we were actually seeing is that the only packets lost are the ones that were actually on the wire at the time of the break. This goes into the next thing that a communication officer does not usually see. You usually have to sacrifice speed and performance for security. The end results of the CEDS, Watchdog, and SDN project was a system that was denied by default, ultra-fast healing, programmable system that still interoperated with traditional Ethernet. And the part that I am really excited about was the security is the visibility of OpenFlow and SDN offer the user who creates granular flow rules. More on this in a little bit, but I want to describe the difference between traditional SDN and OT SDN. Traditional is dynamic and is used by data centers or high-speed backbones to dynamically choose the most efficient path for a packet to travel. A packet is sent to the flow controller, and the controller will dynamically send it based on an algorithm. OT-SDN is designed statically. We predetermine the path so that we can deterministically guarantee a packet will get to its destination on time. Additionally, even if a flow controller had a catastrophic event, flows are retained in the OT-SDN switch. For example, if there was a power loss with a control system, the SDN switches would reboot quickly and communication would begin flowing without having to wait on the Windows system or the operating system of the flow controller to catch up. The flows would already be communicating. The system looks much like this. A flow controller that is OpenFlow 1.3 capable, such as the one that we created with SCL 5056. In this example, it is installed on a substation hardened and ruggedized SCL 3355 computer running Windows Server 2012 and the SCL 2740 OT-SDN switch. The switch has been KEMA certified to exceed 61850 performance requirement. This is a family of protocols that are used typically in energy environment. A couple of them being protection traffic and then one of them being automation type traffic. This is a switch that can operate from -40 to 85 Celsius with a wide range of humidity. It has been vibration tested and ESD tested to the point of breaking. The requirements for a substation is 6 kilovolt contact and 8 kilovolts in the air. We certify our products above and beyond to all of them being 8 kilovolt contact and 15 kilovolt in the air. And all of our devices, most of them can handle 12 kilovolt contact and 20 kilovolts. So we more than double the requirement to ensure that they have the most survivability during a power type of event. When I talk about matching criteria or flow matching rules, I like to show this slide. We can make rules that match on one or all of the following match criteria. From the physical ports to the MAC addresses, source and destination, to the IP, source and destination, to the ether type, and the ports being used. A good example would be rewriting a rule that said a packet is coming into port 10, must have a source MAC of X and a destination MAC of Y. It would also need source and destination IPs. And if we were sending the packet to a web server, the destination packet would need to be 443. If this matches the criteria, then send that packet out port 12. Otherwise, drop it or send it to an intrusion detection system. The return packet with the reverse would be the reverse of all the above, and the source packet would be the source TCP packet would be 443 from the server back to the client. So it's kind of a quick review of the cybersecurity event as opposed to comparing like traditional networking to software-defined networking. Is this one employs a denied by default architecture, where traditionally a network switch comes with no security, but then you can tighten it down with VLANs or MAC address filtering or other things, but this goes up and above and beyond that, where now you are denied by default from the start. It also eliminates the MAC table on the bridge protocol data units spoofing, and it greatly improves the situational awareness, because if you make granular flows, you now know the number of packets and the number of bytes that have gone through a flow. This becomes very, very powerful in that machine-to-machine traffic in an OT system. You have that ability to granularly look at that traffic, and if I'm only supposed to send you one packet every second, that's 160 bytes. At the end of an hour, you should see 3,600 packets. And it varies. One of the importances for 61850 is to actually prove that 99.99% of those packets got to their destination. This is kind of a typical example. The big thing that I want to highlight here is the fact that when you send a packet, there are no loops. There are no blocked ports like in a traditional network. I can send my primary packet through Goose 1, through the middle switches from the right-hand relay to the left-hand relay. I can send my secondary via fast failover through the top. And then, because Goose 1 is my primary protection traffic circuit, I don't want any other traffic on it. I want to leave that the majority of the time open just for protection. So I can use my SCADA traffic through the bottom 2740 switch, and I could do my engineering access via the top 2740 to be able to have engineering access into the relay. But again, the main part to prove here is that you are in total control of that network. And on this one, what we're showing is kind of like the basics of the topology view within 5056. The left-hand side of the switches and the devices is showing your physical path, and the right hand is showing the logical path. So in this one, we need SCADA communication from the SCADA device to talk DNP, a type of automation type traffic in energy control systems, to talk to the relay. And we have that set up for both ARP and DNP3 packets. On the left-hand side, it shows that there are single points of failure with only having this thing connected to the switch one time. What we typically see in energy control systems is this is about backup could be serial communication, or you might have another Ethernet port connected to like a parallel redundant path to another separate network, depending on the level of importance of that substation. On this, so basically this network visibility, which I was alluding to before, allows you to do so many things with that traffic, especially if you start integrating, and I'm going to go to the next slide and talk to this, where you start integrating other products into our API of the 5056. If Dragos, which with their system information event monitoring system and their intrusion detection system, is able to also look at the statistical information. If you say that there's nobody supposed to be doing engineering access between the time of day of 10 p.m. to 6 in the morning, and if you see anything happening with engineering access flows during that time period, then I want to be immediately notified. That would be Dragos or other type of IDS providers that are reaching into the 5056 to look at that information to really say something significant is going on. Another type application for that is if all of a sudden we start seeing dropped flow traffic, traffic that doesn't meet a match criteria within our network, we can immediately send that to an intrusion detection system to be all PCAP'd and recorded to figure out where this traffic is coming from. Was it supposed to be there? And if it wasn't, why was it? So you can really reach ground truth quickly, whether it's a cyber event or just something that was misconfigured or somebody doing something at an inappropriate time. To sum this up, the SCM really does a really strong approach in being able to centralize network management, programmatic network testing. When a link fails, we know the secondary path. We know the length of that secondary path, which we can then give deterministically to the protection engineers so that they can formulate that the secondary path is going to take this long as opposed to the primary path. That is important to a power engineer. It gives you simple circuit orchestration to be able to tell what circuits are being used, how they're being used, the visibility of the packets. And it extracts the complexity out of the field devices to make the system more usable as well as more secure. And I believe that is the last of my slides. Steve, pretty much ready for any type of questions to the audience. If I haven't been monitored, I haven't monitored the chat, but I see some chat conversation going on.
Yeah, the folks were quiet during the presentation, Tim. I think they were paying close attention to what you had to say. So we do have a question that just popped up. So it's let me take a look at this. It's endpoint integrity and least privilege communications policy do not imply bug-free application code. Some of those unknown bugs are exploitable vulnerabilities. Is there any provision for analytical behavior baselining beyond the whitelisting in order to detect anomalous usage characteristics?
And then I'm assuming this is in reference to the ExaGuard. Okay. So with the ExaGuard, with the application whitelisting for the code within it, okay, I'll give you a strong example of this. Something that we've been researching with Dragos on is the state of a packet when it's coming into a device. So what we've been seeing with a lot of the current attack vectors, say, is like crash override. They are sending out of sequence or out of state packets. So what we already do in our devices is make sure that the state of a packet being received matches what it should be getting. And what I mean by that, a simple form of that, if I haven't sent you a SYN and you haven't sent me an acknowledgement, I shouldn't be sending you a message. So that would be kind of an example of the way that we do whitelisting of monitoring the state of different protocols coming into our device to ensure that they're not out of sequence. Would be one way that we've been detecting anonymous behavior.
Okay, thanks for taking that. Thanks for taking that question. So I guess, you know, given your expertise in this area, I'm just wondering, like, are there a few things you know, that you think folks should be doing right now in order to try to, you know, defend these operational technology type systems? Is there, you know, so if you were running the world, what would be the, you know, your kind of top three things that you would do right away?
Gosh, I'll narrow it down to three. But the first one that has to be done in the OT environment, any control system, energy, power, sewer, fire suppression systems, CCTV, all the physical security systems, is asset management. You've got to know where these devices are. You need to know the firmware. You need to know the IP. You need to know the points of contact from both who's managing it on base to who is your vendor provider, and does that vendor even still exist so that you can get support from them. And then I would push the vendors to the point that you knew all the different types of modules that are within the firmware that exists. A good example of this would be like Heartbleed. When OpenSSL 1.3 came out as a vulnerability, SEL keeps good management of their devices as within our supply chain portion of our devices and the development lifecycle of our devices, that we could instantly tell that this OpenSSL affected 4 of our devices. And we immediately notified our customer base privately, and then within 30 days, basically had a fix for that. But that's knowing where your assets are and knowing the right questions to push the vendors on, especially from a DoD point of view, where you might know a vulnerability before, a common vulnerability before the rest of the world does. A second way is the segmentation and connection of OT to IT corporate, whether that's corporate, whether that's NIPR, whether it's the cloud, is one, no, these systems should never be directly connected to the internet, no matter how badly Joe Schmuckatelli wants to access that device by his cell phone or by any type of insecure methods. There should also be some thought behind how to get information from the IT into the OT. I would look at this as a sanitization process, the same as how I would move a file from the NIPRnet to the SIPRnet to make sure that I wasn't either moving vulnerability up from the NIPR to the SIPR. I would want to have like a read-only copy that got brought into the SIPR. The same thing, I would want a read-only copy from the OT brought into the IT and vice versa. Those processes need to be matured. And then finally, the one that I see is the lead attack vector is the operating systems, whether it's Windows, Linux, whatever flavor. These systems need to become part of somebody's oversight and managed and maintained. And I know we go back to price, time, and dollars. We don't have the right price or the right people to be able to move into the OT environment, nor do we have enough people that the people can do their IT job and move into the control system environment. That is definitely a work in progress for DoD as well as every public utility and everyone out there. But the majority of these vectors are unpatched Windows machines or Windows machines with vendor code that cannot perform on a hardened Windows operating system or CentOS operating system or whatever your flavor is. Those would probably be the ones that I think both vendors and DoD and all customers really should be paying more attention to.
Thanks. Yeah, kind of maybe following up on that last item there. Given the length, the long duration life cycle of these OT systems, I was talking to some other folks, and they were talking about some code that got written 30 years ago, and it's not documented, and it's doing the job, but nobody exactly knows how it's doing the job, and but it may not necessarily be fully secure, and so to possibly go in and change that code to make it
Yep.
opens up other. Go ahead.
Sorry. Yeah, I have a perfect example of that. There was a base about a year and a half ago that had an SEL device operating for 15 years. The person that always maintained it had been moved on or retired, and the base called us up and asked us, "Hey, when I walk into this room, this light is always green, but today it's red, but I have no idea what the device does, and I don't have any idea to know why this alarm is going off." And so that required our government engineering service team to go out there and support them and figure out exactly what was wrong. But they really had no visibility of where all those devices existed or how they communicated or what they were actually doing. I do see John Butler's question. The DISA ATL. We've been working a lot with OSD on whether...
Tim, could you state the question before you answer it?
Sure. He said, "I heard your statement about RMF with regards to DoD systems. but there are still requirements to choose information assurance devices from DISA APL. Not sure how I can sell security products on my program. How do you reconcile? This is something that we have been actively working with OSD, USAFE, and other services for about the last 3.5, 4 years. Before it didn't matter. I believe DISA, in my opinion, DISA does not currently have the capacity to handle OT devices. If we wanted to start doing this now immediately, to get devices through DISA APL is going to take you between 9 to 24 months. So that's an issue that needs to be solved. I know that OSD has an idea of a control system approved product list. And then I guess one other caveat on this, I think SEL is pre-positioned because we've been working on it for so long, but if we wanted to look at all the different control system devices that you need to purchase to ensure that they're secure for control systems, these devices, there's a sanity that has to be thought of. Do you really want all that goo in an HVAC system to increase a device that costs normally $100 to $500? Does it need the security? Well, yes. I mean, Daryl Hagley from OSD, his favorite example is to talk about a location that had an HVAC in it that the HVAC actually had a microphone in it. And because the HVAC was connected to an IT system, they didn't want it on the nipper, so they had it on a separate system, but that system was connected to the internet, and we can only imagine where that microphone was communicating to. So yes, there needs to be something done, but it's how do we do this in bite-sized chunks to get rid of the legacy devices that we have, to maneuver all the vendors in a way to move forward. And it's tough. The DISA APL, it's taking us, we've been trying to do one set of products onto the DISA APL, and it's been taking over years. So it's very difficult and a big challenge there. I got several other examples of that would be good, but I'll kind of leave there. I think it's people first. We really need to be thinking about how to train or obtain the right amount of people to move into these control system environments. One thing that I had that I kind of skipped into my presentation was I love the ideas of what the Navy is doing with, and the Navy and the Marine Corps are doing with their ICS enclave. They are looking at putting the devices that are needed typically on an IT side, a Windows System Update Server, a SIEM, other things to manage multiple control systems underneath them. That is important. You do not want every control system to have to come with its own domain controller or its own type of centralized authentication. Whoever's going to finally inherit that from the people side is just going to just say, this is too much. There's too many different things I have to learn. So that's important to get a grasp on, of the centralized type of authentication that DoD wants in these devices. Does it make sense? And understanding that every time that you want something tested by a vendor, whether it's NIAP, whether it's JITIC, whether it's FIPS, all of it comes at a very high price tag, and requires a lot of cycles for us, where we could be spending it on creating the next great device. It's spent on making sure that the device is up to date with the current changing security factors. So all that kind of plays in. I saw from John Butler about the Air Force. I have heard of the COINE, the coins. That is very powerful too. We've been wanting to kind of, I have not had time, but I have been wanting to build a relationship with somebody on the Air Force side. We've been doing that exact testing with our system that is at Mantech for the Type RMF, where they are using that ICS enclave and the parts and pieces to show where our system can interact with with what you're talking about with Active Directory, with SCAP, with McAfee. And I think all that very important to get a hold of at either a base or a service enterprise type level of how you're going to deal with it. How are you going to move these system events that are on the OT side into the IT and to be able to view Nipper, Sipper, and your COPS and your OT COPS all at the same time? But leave it. I have one interesting closing thought that OSD always briefs. If you are a base that has 2,000 devices, that's your comm equipment, you have enough people to manage the 2,000 devices, you will typically divide that number by 2, and you will have 1,000 physical security devices, motion detectors, door contacts, CCTVs that are all IT related that are truly being secured and monitored. But now take that 2,000 number and times it by 10, and now you're talking the number of control system devices, whether that's a building automation system, the fire suppression system, and building metering system. Now you move up to 20,000 devices, many of these things that are meant to last another 10 to 20 more years, and you've got to figure out how to prioritize these risks.
So on that, following up on that, do you see, like, could the SDN technology be helpful, beneficial in trying to manage those, those number of industrial control system type devices in that example?
Yes, a couple different ways. The first would be the fact that once you start using the SDN, you have to know what is communicating with what. So that forces people or bases or whoever's managing the devices to know what protocols are being talked and who is talking to who and when and why. That right there will give you a baseline on the network side. One, you'll know your devices. You'll have to know the IPs, the MACs. At that same time, you can get the firmware of these devices. And then two, you'll know exactly who they're talking to so that when something different is happening on the network, one, now it can't happen. So really pivoting within the SDN environment will be limited to communication protocols that are allowed. So what I mean by that is, even if I have an old relay that I cannot turn Telnet off, if I don't make a flow rule for Telnet, you are not going to be able to Telnet into that device unless you were physically there and connecting a computer there. And if I have physical access and I wanted to cause destruction, I wouldn't be spending my time plugging into different ports to see if Telnet was turned on. I would be doing other things if I had physical access. So it's a unique problem set. It's been very interesting the last 5 years working in this environment. It's been a fire hose of learning the automation, the protection protocols, and all the different protocols that are used. And if you turn your mindset of why they're there, you can kind of build an understanding by trying to fight it and say, well, this protocol was never created with security in mind. Well, the next generations of one, especially working on projects with like CEDS, with DOE and other national labs, we're going to get there. It's just not going to happen overnight.
So once again, I think going back to one of the key points you mentioned, it's knowing exactly what assets your system is composed of. Knowing who's supposed to have access to them. What kind of communication is allowable or not. And if you have that overview, I think that puts you in a much safer, secure position. So.
Yeah. And definitely, and once you know that, then that makes you primed to be able to do an SDN-like solution where you would feel the power of OT-SDN having basically what I call a stateless layer 4 firewall between the ports to those edge devices that are going to take a while to come up to full security. But now you can monitor them for when those protocols are being used, or look at the statistical amounts of the flow traffic to see if there's changes. It just gives you a much stronger baseline that you can actually monitor.
Okay, that sounds good, Tim. So I want to thank you for taking the time to put this briefing together and share this information with us. I know you've been busy, and you've been trying to squeeze this into your busy travel schedule. So I appreciate you taking the time. I think this is, the energy systems, the securing those and, keeping them secure is a vitally critical, area. And, I think it's one of our top priorities. You guys are doing some, very cutting edge research and making some good strides in novel developments. And, once again, thanks for sharing the information, and thanks for the work you're doing. We appreciate it.
Yeah. Thanks, Steve. Thank you for the opportunity.
Okay, everybody. Well, thank you for joining us today, and we look forward to seeing you down the road at one of our webinars in the future. Thanks, and have a good day. Bye-bye.